yeah. And that's a good, I won't even worry anymore. Took all my cares, took and kicked them all out the door.
Good afternoon, everybody. Thank you very much for attending. Internet of Things, that's what we're going to talk about today. And it says embedded up there as well. Well, Internet of Things and embedded are very tightly coupled. What is Internet of Things? Well, I thought a great example was if you had the opportunity to attend the Monday morning keynote by the Freescale CEO. He was talking about Internet of Things. And the example he cited was, he says, someday in the not too distant future, you'll be getting ready to head home from your office after a hard day, and your house will sense that you're getting in your car, and it will turn on the air conditioning and turn up your favorite music. It'll cool down your favorite beer, and you get home and everything's all ready for you. But he kind of stopped there, and I was thinking, well, wait a second, you missed the most important part. After I drink the beer, I want something that's going to go down to the gym and work off those calories. So anyway, but Internet of Things is basically anything, any device being connected and talking to any other device, usually through the internet, but maybe directly or through some kind of communications channel. What we're going to focus on today is talk a little bit about what are some of the requirements for Internet of Things embedded from a processor standpoint, from an application standpoint. And then also from an implementation standpoint, if you're designing an SoC, what is the implementation solution from a physical IP perspective? What kind of libraries are available? What kind of memories are available? What are the requirements there? So it's kind of a womb to tomb implementation story, if you will. So Internet of Things, as I mentioned, it's any imaginable type of any device talking to any other device. For medical is a really good area. For example, you could have a heart monitor attached to you, and what happens? You go to the doctor, and you say, "I've been feeling faint," but of course, when you go to the doctor's office, it never happens. You never get the symptoms when you actually are in the doctor's office. In fact, you feel pretty good because you're in the doctor's office, because if you keel over dead, the doctor's there to save you. But what the doctor would really like to do is see your data, your heart data, your blood pressure data in real time over the last week or so. So you could have a monitoring type of device that could be always connected or gathering data and sending information to your doctor's office. In the car, smart cars and smart safety systems, things like that. In the home, of course, the dishwasher could be set up ready to go, and then when the energy company, the power company says, hey, you know what, we got very low demand right now on our energy grid, 2 o'clock in the morning, it kicks on your dishwasher and it starts washing dishes. So there's really some good practical examples of Internet of Things. From an enablement standpoint, typically what you'll have is you'll have a microcontroller, typically like an M-class type of a microcontroller. And then you're going to have some kind of a sensor, communications. It could be wireless, Bluetooth, Zigbee, some way to communicate, and a hub to be able to get information in and out from the internet, from your house to the internet and back again, and so on. And ARM, of course, with our ecosystem of over 1,000 partners, is working to enable and to facilitate a complete ecosystem, if you will, of partnerships to be able to make this happen. So if we look at from a system perspective, SoC perspective of Internet of Things, clearly it's talking about increasing interconnectivity, higher control data performance from a computing standpoint, wanting to do more information so you don't have to have too much bandwidth going over the internet. So there's always a question of, I'm sensing information. Do I want to pre-process it first? Those types of things. Increased code store. Think about engine control, for example, in a car. How much more complex it's become, especially with these hybrid types of cars. The code store is driving the need for more flash, which is driving people to go from 180 nanometers to 90 nanometers down to even we're seeing customers looking at 40 nanometers now for embedded flash. It's not that they have a lot more logic functionality, but it's because they have a lot more code instructions that they need to execute. And it's really the embedded flash that's driving that. And then, of course, analog devices, the sensors, the RF, also need to keep up with the requirements as well. Energy efficiency, critical, especially for the mobile devices. If you're wearing a device, you want it to last at least all day, if not several days. And also we have these things called energy harvesting, where some of these things may be even solar powered, where you don't even have a battery on board. And then of course wireless connectivity is really key. From a processor standpoint, 16 bits is running out of headroom. You can certainly get higher performance out of it, but the problem is the faster the clock speed, the more power consumption. So 32 bits becoming more and more important area in the Internet of Things implementation. So if you look at the classes of processors that ARM offers here on the right, the applications processors are the high end. That's what you typically see in the mobile phones, in the servers. Those are the ones that are really compute intensive types of functions. In the mid-range are the embedded processors for real-time processing. They have the RTOSs, things like that. And then on the lower end is the Cortex-M. The M-class devices are the ones that we really expect to be seeing taking off in the Internet of Things, in the embedded space. And one of the nice things about the M's is that they share a common instruction set architecture, whether you're using an M0 all the way up to the M4 and then on and to beyond. So depending on what your processing requirements are, you can select the right core. If you want very low cost, very performance isn't critical, then of course you'd start on the bottom left there. As you drive up to the right, typically you have applications requiring more performance and so on, and you go up to the M3, M4. So it's important to have a complete range of solutions and not have to worry about migrating your code and things like that. So what are some of the applications for Internet of Things? There's a whole myriad of them. This is just kind of a sampling of them. Things like motor control, smart metering. It's interesting because in California, when they put the smart meters, the digital meters on, everybody's power bills went up. And clearly, people weren't using that much more energy. And I wondered this myself. I said, why did my bill go up by 30%? Well, the reason is because it turns out that depending on the time of the day that you use the energy, the rates are going to be much higher or much lower, of course, depending on the demand on the power grid. So by knowing what the when energy is cheap and when it's more expensive, and actually building devices, smart devices that actually understand that and can talk to the power company, you can now have your dishwasher set up or your laundry set up to go. And what happened is the power company sends a signal and it'll turn on that appliance during a very low energy demand, maybe at 2 o'clock in the morning when there's plenty of energy available. You'll save cost in terms of how much energy it took to run that load of dishes, and the power company won't have to go out and build another power plant or use some very expensive coal power, high polluting type of power source. So that's just a practical example of why Internet of Things and work can be used in a very practical manner in the smart home. Things like power management, the light sensors you've all heard. Why do the street lights have to be on all the time? If it can just sense when a car is coming or a pedestrian is coming and turn on then and then turn off, that can be really important for saving. So it's not about increasing the amount of things that are going to consume energy. It's actually about how to consume energy in a much more efficient way, if you will. Medical instrumentation, I gave the example of the heart monitor. Automotive, clearly a lot of opportunities there as well. So so far we've talked a little bit about, from a processor standpoint, from a systems requirement, what's required. The next area we're going to focus on is actually from an implementation perspective. What type of physical IP do we offer to actually help to implement the Internet of Things from a chip perspective, to be able to do it in the most power optimized way, performance optimized way, and cost and area optimized manner. So if you're using an M0 plus class core, this is typically where you're going for very low power, the lowest power. You're not typically running at very high speed. You'll have something that's kind of in standby mode most of the time, and you just care about making sure that the core operates efficiently when it needs to be turned on, but the rest of the time it'll be sleeping. So for those types of applications, we have ultra-low power standard cells with what we call power management kits. These are typically 7-track libraries implemented in a 90 nanometer or 180 nanometer low leakage process. We have what we call thick gate oxide libraries, TGO libraries. What these are actually libraries that are built using the I/O oxide, the 3.3 volt I/O oxide that are already available in the process. And the advantage of that is that they significantly reduce the active power consumption for circuits that are on all the time. For example, if you're waiting for something, a trigger to come in, if you're waiting for something to come into the field of view and then you want to send a message, that's what active always-on circuits are about. And then the memories that need to go with that, we have ultra-low power memories. So our memories typically today have light sleep, deep sleep, and power down modes with the memories. In fact, what we've done is we've taken our most advanced memory capabilities from 28 nanometer and actually backported them to 90 nanometer today. So that's something that we're really unique in that case. Is we've recognized that there's a lot of new applications coming at 90 nanometer, 180 nanometer, and we're actually making investments in those areas. You know, most people are talking about FinFET, which we certainly are working on FinFET. But there's also a whole new wave of applications coming in the 90 and 180 nanometer and 65 nanometer range. The next area is in low cost, where cost is absolutely critical. Typically, these devices will be very small, less than 2 millimeters squared from a silicon standpoint. They'll need to cost about 25 cents or less. So what we have here are what we call area optimized platforms. So these use our ultra-high density standard cells, 7-track libraries, the high density memories. These would typically be single port register file memory devices. And that's where the memories are optimized for very small area, not so much for speed, but for small area and very low power. And the typical nodes for this are 55 nanometer, 90 nanometer, 130, 250 nanometer. So you'll see a common theme here is that none of these processes are lower than, say, 40 or 55 nanometers today for these embedded applications. You don't need those advanced processes for these types of applications. And finally, from an implementation standpoint here, for the performance types or the computing types of embedded Internet of Things, we have the Cortex-M 3 and M4. Here we have what we call the high-density standard cells. These are typically 9-track libraries. They're optimized more for speed than they are for power. The memories, same thing, optimized for speed. And we also have ultra-low power in memories and logic for where you don't need that speed. You can still use low logic. You know, one of the things people don't really understand is an SoC is actually made up of a whole bunch of subsystems. And so what you really want is you want to have the right memories and the right standard cells where you need the performance, but then you also want to have a different set of memories and standard cells for the low power parts of your SoC that aren't on all the time. And so that's why it's important to have a complete set of libraries from memory and logic to be able to implement these things. And again, the typical processes for high speed are typically the G-like processes as opposed to the ultra-low leakage, low power processes that are available from the foundry. So very specifically, as we look at the chip, you look at the different building blocks there. The ones in yellow there highlighted are the ones where ARM really participates. So of course we have the Cortex-M processor that needs to be implemented in silicon. We have the memories, which are the SRAMs, and the always-on block of logic. This is where you have the sensor circuitry that's always keeping an eye out to see if something's going to trigger an event. So for implementing the Cortex-M processor, this is typically something where you don't really need high performance, but you really want to make sure you get low power and small area. We have the 7-track libraries with the power management kit. We have the base library for implementing the minimum, area efficient processor, and then the power management kit with dynamic voltage and frequency scaling, retention mode, and clock gating. These are techniques that we use to further reduce the power consumption. So even if a part of the processor isn't running, we can shut it down, or parts of the memory we can shut down, and other parts that are running, we will have them active. The next area is to look at the memories. We have two major types of memory architectures, what we call single port register files and high density SRAMs. The high density, high speed SRAMs are where you need larger memory blocks and generally higher performance. If you're really focused on low power and you don't really need more than, say, 100 megahertz clock speed, then you'll typically use the register files to implement those functions. And typically, you can generate the same instance sizes with multiple compilers, and one of those instances will be optimized. It may be a 256K instance. One could have been optimized for speed, and the other one will be optimized for very low power consumption. So you can mix and match depending on which part of the circuit needs which type of memory. And then also, we're finding more and more applications want to run at low voltage to even save more power. So we support underdrive operation. This is where, for example, if VDD nominal is a 1.2 volt, but you want to run at 1 volt, we can actually lower the voltage, the operating voltage, and support the bit cell operation with underdrive capability. And then this is a unique capability, but very important for internet and embedded applications. It's this always-on block of logic. This is where you're going to have this circuitry always on. It's not going to be in standby mode. It typically be on maybe 80–90% of the time. We use the thick gate oxide library, as I mentioned before, to build 9-track libraries, which are a little bit larger in area, but the active power consumption, not the leakage, but the active power consumption is reduced by about 70% by using these thick gate oxide libraries. We also have level shifters because the thick gate oxide libraries operate at a higher voltage, typically about 3 volts, and the other libraries typically operate at about 1.8 or 1.2 volt. You need to be able to shift up and down between the two voltage blocks, and so we provide the level shifter capability with these libraries as well. So that's kind of an overview of the capabilities we have. Now the next question is, well, how do I access this IP and how do I evaluate it? And I don't want to pay money until I know that I actually need to use it, and maybe I don't want to pay any money at all. But we have a design portal called Design Start. What this portal is it's a place where you can go log in on the ARM, www.arm.com, and it'll actually give you sign up for it if you haven't already, and it'll give you access to all of the front-end views of all of our physical IP. So you can actually download the compilers, download the library views. It has all the models that go with them. You can create the data sheets, and you know exactly what the power, performance, and area specifications are for any particular instance or any particular logic block that you want to evaluate. For TSMC, much of the IP is fee-based. You can evaluate it for free, but then if you want to actually tape out, then you may. Some of it's free and others fee-based. On an IP by IP basis, it'll tell you whether it's free or fee-based. For other foundries like Global Foundries, SMIC, and so on, those are most of the time free IP. So you can, the foundry's already paid for them, they sponsored it, and then you can use it actually for free in your design. So, but anyway, this is the web portal. This is where you can start doing the evaluation and evaluate all the different types of IP. So that's kind of a summary of what the requirements are for Internet of Things embedded applications. We reviewed the different types of processor types, the applications, and the implementation solutions, the libraries we have available. That concludes the formal presentation.